some simulation exercises, and these simulation exercises will be done in LT-SPICE. I'll be putting the library files that are needed for these, the model files that are needed for the simulations in the Moodle page, or even in the Teams page. I can just put it up so that you can use it. What we will do is we will kind of go between simulation and theory and try to see how things work. Okay, all right. So now let's maybe just get started with the simulation part of things. Let me, right, okay. So here what I'm showing is basically this is a very simple circuit. This is to show you uh, uh, the DC parameters of a NMOS transistor. So I don't know how many of you are fully familiar with LT-SPICE. You can go to component here, okay, and you can choose basically NMOS 4, okay, which is a 4-terminal NMOS device, or you can choose a PMOS 4, which is the 4-terminal PMOS device, as the case may be, right? So in this case, I have already chosen a NMOS 4 device. Now you can see that I have some two dot include files here. Okay, the first one is a 65 nanometer file. I'll be giving you this .lib file. So what you need to do is to basically create a folder, okay, and put these two files into that folder, and create all your schematics inside that folder, okay, so that it will directly reference it. Of course, you can also put it somewhere else. Then you'll have to include the path. That is kind of obvious, okay. So you can just put a dot include statement here, right? And this is the SEL 180 nanometer file. Now, let me just show you the structures of these files. Okay, so this is the 180 nanometer file that I will send it across to you guys. Okay, now N18 is the name that I have given for the NMOS. All right. So as I mentioned, although for the purposes of classroom teaching, right, or if you look at any of the textbooks, you see the square law equation being given. Now, such an equation really is a very approximate one. In fact, as I mentioned in one of the earlier classes, the um, the threshold voltage itself will change slightly as a function of channel length, right? And also the mobility and other things, they keep changing. Okay, so you cannot really estimate mu and Cx. A lot of students try to do that. They try to run some simulations, and they try to extract the value of mu and Cx. They try to extract the value of threshold voltage. But even if they do that, moment they change their width or the length, what happens is all their calculations which they have done, it all kind of goes out the window, because the equations are very much complex. And you can see for a single NMOS device, these are the set of parameters that you have. All right. So you literally have so many parameters which the simulator uses just to calculate the device behavior for a single NMOS transistor. All right. So here you can see L min is 165 nanometer. This is the 180 nanometer technology file. Okay. So minimum you can go up to 165 nanometer. Okay. And the maximum here is 500 nanometer. All right. So you cannot go beyond 500 nanometer as your this one, okay. And the width minimum is 205 nanometers, and the maximum is 500 nanometer. That is width per finger, and of course you can use more number of fingers and other things you can increase, okay. So you can see that it's a level 49 file. It's a 3.24 version of the BSIM model, okay. And you can see VTH naught is around 366 millivolt, all right. But this is VTH naught. You have all other kinds of, LVTH naught, WVTH naught, PVTH naught. So there are a lot of other parameters that come into the picture to calculate the actual threshold, okay. So this is not the proper threshold voltage. When you simulate it, you will see a lot of other parameters. So you can see a whole bunch of parameters, which is why we depend on simulators to do our analog design, okay. And same way, you have the PMOS model. Here it is given as P18. This is the name that I have given. In fact, it did not come with that name. Because that is what we'll be using. This is a lib file. The other one is this is the 65 nanometer UMC model file. You can say that this is a level 54 thing, and this is a BSIM 4.5 version. Okay, this is a more advanced model file than the previous one. Okay, and you can see it has a lot more parameters. All right, so this is for, so here what I have given is I have given N65 and P65 as the model. I think for now I might give you guys only the SEL1, and also please do remember these files are highly confidential. Okay, so please don't take it and put it in any public domain, that is illegal, and these files are given purely for the sake of academic simulation exercises for this course. That's it. Okay, please do not share it with any of your other friends, and also please do not put it in any public domain. Okay, these are highly confidential. Okay, now what I have done is just right click on this device. The model name here you have to change. Okay, so let me just change it to N18 here. So the width, let me just put 180 nano. N stands for nano. Let's just keep the width as 1 micro. All right, and so automatically it will update here. Okay.
Sir, how do you include the libraries here?
Okay, so I think you can just add some text file here. Just go to add text, and then here you can just dot include, and just copy paste that name. Okay.
Okay, sir.
I think you have to put it as a spice directive and keep it, not as a text file. And to delete it, just use that cut thing. Okay. So go to
Okay, sir.
edit, add text. That's the thing. Okay. Now, what I have done here is I have instantiated, as I showed you. You can go to component here in NMOS4. If you click OK, it will put something like this, escape. Right click this, you will get these things. It will have some students make the mistake of just leaving the model name as such. Then it will just take some level 1 MOSFET parameters that by default it is stored in the simulator, and you'll get all weird answers. All right, so don't do that. So you can put N18. Channel length you can basically give 180 nanometer. Just give N, don't put meter and all. Okay, 2 micron or 1 micron, whatever. Okay. Anyway, I have already kept this, so that's fine. Again, you can go to component and basically take a voltage source, right? I have put one voltage. So here you will see that there is something called as voltage. Okay, so this is your voltage source. I have put one voltage source here. I have put one voltage source here. Okay, right click on this one. I have just kept it as a DC one. Okay, so here the DC value I have given it as 0.5 volt. So for a 180 nanometer device, the typical supply voltage is 1.8 volt. Okay. Now, if you click on advanced, you will have other types of things, pulse or sine or exponential, all these other types. But here I'm just using, small signal parameters are also there. Right now I'm just doing a DC simulation. Okay. I'm just giving 5 volt here. Here I'm just giving 0.3 volt. The reason I'm giving 0.3 volt is typically when you design your op amp and other things, and when you, put a let's say for example, you're designing an op amp, typically the VDS will be around 0.3, 0.4. That's what you will design for, right? You will not design for a very large value. For example, in a 180 nanometer, you can have something little higher, and I've characterized it. In fact, you can do it for different things. So for example, right now, let me just put 1.8 volt, right? And so here, what I have done is basically, so here you just go and right click, you can start editing. If you put semicolon, it is a comment. All right. So let me remove the semicolon, put a dot. Okay. That means this is active. I'm going to just, maybe what I'll do is let me show how to do it from scratch. So let me just remove this. Okay. All right. So this particular statement is also commented out. Right now, I'm just doing a DC operating point simulation. .op means DC operating point simulation, which means for these bias conditions, what is the drain, what is the voltage and current and GM and other things. Okay. Now, how to run the simulation? It's very simple. Just go and hit run, right? So it will run, and this is giving you your operating point. Okay, basically operating point means at the DC what is the amount of current, what is the voltages. So it is showing the VDS is 1.8 volt, that's what I said. VGS is 1.5 volt. ID is how much? 2.26 microamps. IG gate current is 0 obviously. The bulk current is some 10 raised to minus 12 picoamps, forget it. IS and ID are essentially the same. I of V2 is the current drawn from this supply V2. I of V1 is the current drawn from the supply V1, which is 0. This one is the same thing. Okay. So the negative signs are because of the direction of current. All right. Now, what also happens is as you close it, it gives you, a whole set of other parameters. All right. In fact, you can also go to this location right now. There is a .log file. Let me also show you how to see that. nmos underscore char is the schematic name. You will see one log file. Okay. So I think this is the log file, right? You can open it here or you can also open there. So this is how it is basically running. Here you can see the ID for this transistor M1. ID we saw already, VGS, VDS, VBS and other things. The threshold voltage, it is around 496 millivolt. Okay. So this is the actual threshold voltage after the big calculation that it has. Okay. Now I want to introduce to you this parameter called as VDSAT. Okay. Now what is VDSAT? Now typically for saturation to happen, we say that VDS should be at least equal to VGS minus VTH, right? So in this case, what is VGS? 500 millivolt. VTH is 496 millivolt. Okay, what is VGS minus VTH? 4 millivolt, right? So your VDS should be greater than or equal to 4 millivolt in order to be in saturation. That is according to our typical equations that we have seen so far. Okay, but in practice, what happens is the expressions are different. Okay, because for all these deep submicron processes, the equation is more complicated that you cannot do hand calculation. Now, this parameter is calculated and is given as VDSAT. Now, this VDSAT, as you can see, is 6.9 e raised to minus 2, which is nothing but 69 millivolt. So, what this is saying is that if your VDS is greater 69 millivolt, then you are in saturation region. So, when you are actually designing circuits, right, when you are actually running simulations and designing circuits, you do not look at VGS minus VTH. If you look at VGS minus VTH, you will get completely crazy. Okay. So, I mean, you'll get completely confused. All right. So, don't look at that. Look at this VDSAT. Okay. Your VDS has to be greater than VDSAT, which is calculated by this simulator. Okay. Many times when you are doing your simulations, you have to look at this log file, because when you go through this log file only, you will see the all these DC parameters, and you'll go and check whether each of your transistors are in saturation or not. Okay. This is GM. GM is our small signal transconductance. So the transconductance here is 44 microsiemens, right? Now GDS is nothing but 1 by R naught. Okay. So 1 by 6.03 e minus 7 is your R naught. GMB is, we have already seen that parameter. CBD is the bulk to drain capacitance, bulk to source capacitance. Okay, it's just given 0 here. CGS overlap, the overlap capacitance is given. CGD, CGS, CGB. Okay. Now these set of parameters are literally the actual capacitance. Basically what it means is the dQGD by dVGB. Okay, the way the simulator calculates capacitance, it takes dQ by dV. C is Q by V, right? So the way it calculates capacitance is dQ by dV. So here it is nothing but the gate to drain charge with respect to gate to bulk voltage, right? So you can see that these are all in the terms of either femtofarads or point some femtofarad. Some of them are very small. Okay, usually you don't go so deep into these things. All right. Okay, so this is our operating point. All right. Now going back to this. So for example, okay. All right. So ignore these things. Basically, it's saying that it's not able to recognize certain things. Okay, all right. Now I don't need to, do this. So let's say I want to create some simulation. Go to simulate, edit simulation command. All right. Now what I want to do is I want to plot your ID versus VGS. So what I will do is I want to sweep the D. So for ID VGS, how do we do? We fix a certain value of VDS, right? And we sweep the value of the gate to source voltage, right? So I am giving a DC sweep here. All right. So the first source, it asks for the name of the first source to sweep. The name is V1 here. Okay. So V1. Now type of sweep, you can have linear, octave, decade, list. Okay. So basically this is the way in which it will do. Okay. So octave means it will go in terms of, in terms of 2. Right now I'm not doing that. I'm just giving a linear sweep. So I'm starting from 0 volt. I'm going all the way to 1.8 volt. Okay. I want to do it in increments of, let's say, 0.01, 10 millivolt increments. Okay. I can even do for 1 millivolt increment. That's not an issue. Just fill up these things, click OK. You will get this statement here. Just left click somewhere here, it will drop it. Now you can notice that the moment I drop this, automatically this got disabled. Okay. Semicolon is this one. So just save it and hit the running man. All right. So it has run. This is your log. Basically, it has, run whatever it is supposed to run. Okay. Now, what I am interested is basically I want to find out x-axis is basically my sweep, which is VGS. I am interested in the drain current. So you go here to close to the drain, you can see that the cursor changes. So if I plot here, it is a voltage. If it becomes a circle, it is current. So I just click there, it will plot here. Okay. Now this is your ID versus VGS. So you can see that this is your subthreshold thing. Now you can add a cursor. How do you add a cursor? I forgot actually. Actually, it's a very simple. Is it double click? No, not double click. I forgot how to add cursor. I did it earlier. And okay, anyway. So you can basically, if you hover over it, you will see that, you can also zoom in, right? You can go and fit it back. So here you can see that this is the subthreshold place, right? This is your, quadratic thing. This is where it becomes linear because of your velocity saturation. Okay. Now you can go and view what is this grid. Okay, draw cursor, position, edit. Hey, you guys, some of you have used this, right? So do you know how to add a cursor here? Not this mark data points. I think it's not.
Add trace maybe
Sorry?
in the right click menu there is add trace something.
Oh, okay. Actually, here you go and okay, attach cursor, right? You just go and right click here, right? Okay, somewhere. Just click on this one. Got it. Okay. Just click on the waveform here. You get a cursor, right? And you can move this cursor and you will see. So I added two cursors now. Okay. So you can move this cursor and then you can, see the value. All right. And it will also show you differential cursors and so on. All right. So let's close this one. Okay. So this is how you can do. All right. Now the same way you can also plot. So what I want to show you actually is like instead of sweeping V1, let me sweep V2. Okay. Now for if I sweep V2, what do you expect? Basically, you will see the output characteristics. You will see something like this, right? Now you can see that if you go and click here, yeah, you get your cursor, right? So this is where the horizontal is what 69 millivolt or something like that was our VD sat, right? So till this point it is in triode region. Okay, 69 was yes somewhere here, right? Beyond this is the saturation region. Now you can see that from the edge of saturation, let's say from here, it is the value is some this is the one. Let me put one more thing here, maybe somewhere here, right? So from let's say 131 millivolt to almost close to 1.8 volt, the current is changing from 1.2 microamp to 2.2 microamp, right? Vertically it is changing by 1 microamp when it is going with a voltage change of this one. So here this is a 180 nanometer technology node. So just keep in mind it is kind of changing like this. Now the same thing, if I go and run it with instead of this, let's say if I run a 65 nanometer device, and let's say I put 60 nanometer is the minimum width, okay, and let's say if I run the same simulation, okay, now see the slope. The slope of this, okay, actually I should run only till 1.2 because, okay, so let's save it and let's run it, okay. Now look at the slope for a 65 nanometer technology node, right? The slope is much higher, which means the R naught is very low, right, compared to what you had for a 180 nanometer device. So you can see that the base current itself has changed because the W by L ratio has now changed, right? But you can see that the difference is basically what, 69 microamp for a nominal voltage of nominal current of around 50. So you can see the slope itself has changed so much, right? So this is what I was talking about earlier. When you change your this one, so for example, even if you go back to let's say N18, right, and instead of that 180 nanometer, let's say I am putting a 350 nanometer this one, or rather what I will do is let's keep 360 nanometer and 3 micron, so that the current remains not the same but fairly constant. Here I will go up to 1.8 volt, okay. So if I run this one, okay, here you can see that if you put this second cursor, look at the slope now, right? It's the same thing, same 180 nanometer device. All I did was I increased my channel length, and now my output resistance has increased so much better. And you can see that the delta is so much lesser. It is only some 512 nanoampere change, right? The slope has now decreased so much, which means your R naught has improved. All right. Now, this is what happens this is why we always go for increase in channel length whenever you do a current source. All right. So far we have been looking at current sources. In fact, what simulation I have drawn here is basically it's a current source where the output resistance, basically you can look at the slope and then calculate the output resistance. You can take 2 points, for example, you take any 2 points, you get the slope. This slope, if you take the inverse, you get the output resistance. So what is the output resistance? Is 2.2115 10 raised to minus 7 inverse, right? So what do we get? We get around 4.5 mega ohm. Okay, wow, that's a very large value. Okay, so you get a very good output impedance here. Usually you get in the order of, if you change this to, for example, 180 nanometer, and then you take the same 1 micro and you rerun the same simulation, right? If you take the same thing, you get 5.8 as your this one. So 5.81 5 10 raised to minus 7 inverse. Okay, so this is like, okay, it says 1.7 mega. I'm not sure whether I got it right. Maybe you can just calculate it, right? You can just calculate di by dv or dv by di to calculate your actual output resistance. So it's possible because the current is quite low, the output impedance is quite high. Okay. Another thing I can do is with the same. Yeah. Yeah. Someone had a question.
Sir, with 360 nanometer, you took the width as 3 micrometer. So, but
yeah, I kept the W by L ratio same.
So it is to be 2 micrometer, right? 180 by 1
Oh, I'm
and
sorry. Yeah, you're
360 by 2.
right. You're right. You're right. Yeah, correct, correct. Yeah. So you're right. So the current is also a little higher, right? So for example, if I take the other one, yeah, I think, yeah, my mistake. Correct. So for example, if I increase the width, all right. So I have raised it to 10 micro, and if I'm going to run the same simulation, right? What is my, you can see that my slope is now increased, right? So it is 2.966, 10 raised to minus 6 inverse. So that's around 337 kilo ohms. Okay. So as we saw in the thing, R naught is equal to approximately 1 by lambda ID, which means that as you increase current, your ID will, as you increase current, your R naught will start dropping. All right. So that is what you would basically see. Okay. All right. Now with all these things, so you can, I will give you some simulation exercises, right? So we can, so with that you will be able to see your this one. So right now in the simulation, I just kept a, you know, let's just see where this is, right? Okay. So in the simulation exercises, in the simulation that I did, I gave a constant voltage source. You can put a current mirror, and you can see how your, you can basically look at your output current versus voltage. In fact, the simulation would look something like this. You put a reference current, let's say this is VDD, put some IREF, right? Put a simple current mirror, okay, and connect this to a voltage source, sweep this from 0 to, let's say, VDD, right? So you will see that kind of a behavior, right? So for this current mirror, so in this application, okay, based on what we saw both in simulation as well as from our theory, what is the minimum voltage that this current source requires? So if you consider this to be a current source, what is the V min that it requires? What is the V min that it requires? Can you tell me?
VD sat.
Is exactly VD sat, right? So V min is equal to VD sat. All right. So if you're basically doing a hand calculation, you might say, okay, VGS minus VTH. But now that we are kind of maturing out of hand calculation to using simulators, we will say the minimum voltage is basically the VD sat, because below this current source no longer acts as a current source, right? It is kind of in the triode region, right, where it is going to be almost like one resistor. Okay. So you need at least Vmin here. Now the problem that we were seeing in the last class is that as there is voltage fluctuation here, right? Now what will happen is because of the slope, okay, you are going to have some current here. So for example, when I biased it at, like, when we use that 3 micrometer by 180 nanometer, I think the current was somewhere around 2.7 micro or something, right? I forgot the exact value. Let's say 2.7 micro, and we had something like some, how much was it? Some mega ohm range, right? So we had some 2 mega ohm or 6 mega ohm, something like that, right? So that is your output resistance. All right. Now what happens is that's a very good value. Now the other, when you go for 65 nanometer, or sometimes when you have to design with 28 nanometer or 90 nanometer and things like that, your output resistance becomes very poor. Okay. Now if you want to improve your output resistance, we saw in last class, one of the techniques that we can do is basically to cascode it, right? Now when you cascode it, how does it work? You have a, this is your IREF, right? So this is some VB that you generate in some way, right? And you use something like this. Now when you do a cascoding, now how do you choose, let's say this is M1, this is M2 and M3, right? Now how do you choose VB? VB has to be chosen such that it is equal to VGS3 plus the VDS2, where the whole purpose of this is to make sure, there are two things that are being done here. Okay. One is there is a systematic offset which occurs. Okay. and the second is basically output impedance. Now these two are a little, kind of related, right? If you increase your output impedance, your systematic offset comes down. But there are these two components, all right? Now, what is systematic offset? Okay. Now, the systematic offset is, suppose you did not have this particular transistor, okay, and you had some load here, right? As last class I showed that this can be a differential pair, this can be anything, or if you use a PMOS current, so it can be a a common source amplifier, whatever it might be. There is something on top of your current source, okay. Now, because of whatever happens here, it might have some voltage drop, so that the voltage drop here, the VDS2, is not equal to VDS1. Correct. It need not be equal to VDS1. Okay, and it's very difficult to ensure that it is exactly equal to VDS1. Now, because of the VDS mismatch, what will happen? Let's say ID1 is, let's say mu n C ox by 2 W by L. So, VGS minus VTH, the whole squared, 1 plus lambda VDS1. So, don't laugh at me because I'm writing this equation. This is just for us to, kind of get that understanding, right? So that we understand the problem. Now, what is ID2 here? ID2, if you were to divide it, you will have mu n C ox W over L by 2, right? VGS, the same VGS, VGS1, VGS1, the threshold voltage is nominally the same, 1 plus lambda VDS2. Now, all these things, so if you take ID2 by ID1, I'm taking the inverse ratio, you end up with 1 plus lambda VDS2 divided by 1 plus lambda VDS1, right? So basically you are going to have a systematic error here, because ID2 can be written as this whole factor multiplied by ID1. So there is a systematic error because of the VDS mismatch. Now again, if your output impedance is really high, the extent to which you have a systematic offset is minimized, right? So for example, let's say the system, the VDS, let's take an example. Let's say VGS1 equal to VDS1 is, let us take 0.5 volt, like how we had in the example. Let's say the VDS2 turns out to be 0.4 volt. Okay. Now, if your R0 is good, if your R0 is really high, the VDS, delta VDS of 0.1 volt will produce a delta I which is small, which is very small, which means that the error in mirroring the current is very small. Now, as R0 decreases, what will happen? This error of delta I will start increasing, right? Because as your slope increases, let's say if this is your slope, let's say these are the two voltages, 0.4 and 0.5, the delta I here is very small. Now, let's say you have another curve which is going to look like this, the same 2 points. Now, the delta I here is going to be larger. So, as your R0 drops, your systematic error in your current mirror is going to increase. All right. So, one of the main reasons for going for this cascode is that what I'm going to do is I'm going to put this transistor on top and make sure that my VDS here let's call it M1, M2 and M3. Let's say I'm having some stuff here, right? What this VB is done, VB is chosen exactly such that it is equal to VGS3 plus the VGS1, or rather this is VGS1 is equal to VDS1, and we want VDS1 to VDS2 to be equal to VDS1, right? And so you take your VB to be like this. Now you can, the first simulation that I did, which is ID versus VGS. So what I would want you guys to do is to take that plot, save it as a CSV file, right? CSV file, or you can read it in Excel, okay? And store it, okay? So that you will be able to reference to it. So usually what happens, So what will happen is, so for example, the way we typically do design, especially for these deep submicron processes, is to kind of create a small lookup table. Okay, so even last year, what I asked the students to do is to take some arbitrary value. Let's say W naught is 1 micrometer, and let's say take 180 nanometer. Okay, run your ID versus VGS plot and save it as a .csv file or some format, whatever is possible. Okay. Now what happens is, and I would typically ask you to run this at a VDS of around 0.3 volt or 0.4 volt. Okay. Because mostly when you start designing your op amps and all, this is the VDS that you will budget for your different transistors. Okay. Run it at this one, save it as a as your this thing. All right. And what you do is, you will always see that VDSAT is less than this quantity most of the time. Okay. Now what happens is, let's say I have M3, and I am choosing M3 to have, let's say, a W of, let's say, 5 micrometer and a length of, let's say, 180 nanometer, for example. Now, let's say my current here is 50 microamps, and I want the same 50 microamps to flow here, right? So what will I do? So I will go here and then say, okay, if I want 50 microamp to flow for a W by L ratio of 5 by 180, how much will flow for 1 by 180? It will be 10 microamp. So you will go to the Excel sheet where you have VGS and ID, right? And you will go to the ID column where you get 10 micrometer, 10 microamps. Okay, you will have a corresponding VGS. All right, so that will be the VGS that you will use for your simulation. So for your VB, how will you calculate? You will take, let's say this turns out to be something like, let's say 450 millivolt, for example. Okay, and let's say here you, for 50 microamp, this is turning out to be some let's say 500 millivolt. So your VB will now be 950 millivolt. Okay. Now you understood what I'm trying to say here. Don't use mu and Cox and all that. Okay. If you decide your W by L ratio to be this much, calculate the current for this reference value that you have done. Usually current will scale very well. Okay. So for example, if you have 50 microamp flowing through 5 micron, in 1 micron transistor, if you put, it will be 10 micron. That scaling is very well done. Okay. Whereas the other square law and other things, they do not scale well. W by L ratio scales well, especially when you have the same channel length. All right. So did you understand what I told? So if for the amount of, what is the VGS that you want, the way you calculate is, take the CSV, keep it, use it as a reference for the rest of the course. All right. And for sometimes you might start with the VGS and find out the current and then scale the W by L. Or in this case, you find out, you have the current value, you find out what is the VGS that is required. All right. So that is how you can do. So when you do like this, what happens is, you are fixing your VDS, the VDS2, to be exactly equal to VDS1, and thereby you are, the whole thing, that what you are doing here is, you are eliminating systematic error. Okay. This is the first major thing that happens because you do cascoding. All right. Now, what about the output impedance? Okay. Now, what happens is, you also improve the output impedance. Now, how to calculate the output impedance?
Sir,
Yeah.
sir, that ID versus VGS plot is for like that single transistor, right?
Yes.
Sir,
You
so
take for a,
for M,
yeah.
sir, for M3, then it will not hold true, right? Because the VDS is different for M3. So ID will be dependent on, like it will have a different, the equation will have a different VDS. So that lookup table will not hold true.
It will hold true to a large extent, because what you're saying is VDS of M3 is different. That's what you're saying.
Yes, sir.
Okay, so which is why I asked you to generate the VDS generate this table for a VDS of around 0.3 volt or 0.4 volt or something like that. Okay. Now instead of 0.3, let's say it is 0.25, the delta is going to be very minimal. Okay. On the other hand, if you
Okay,
go and
sir.
generate it for 1.8 volt, then what you're saying is very true. You'll find a large delta. But typically, from experience, you will see that typically you'll budget the VDS to be around 0.3, 0.4, and not more than that. Okay. So yes, a
Okay,
little
sir.
bit of change will be there. Okay. We will also go look at low voltage cascodes and other things. We'll come to that. Okay. Yeah, but to a large extent, it will hold true. Okay.
Okay, sir.
Yeah. Now, how to calculate the output impedance? So first of all, let's look at the output impedance. Let's look at the R out of a single transistor. So what we do here is we go to the small signal analysis. Okay, why small signal analysis? Much of this output impedance stuff is important because you will typically have a lot of there will be some kind of a signal swing happening at this particular node. Okay. Now, or for that matter, let's say you are having this thing here also, you'll have some kind of signal swing happening, right, because of whatever is happening on top of your current source, right. You will have some AC signal coming in, you're doing amplification, you're doing all kinds of things, right. Now because of that, this node, if you call it as node X, right, this node X is going to swing a little bit because which is dependent on the signal that is coming at the input of your, the rest of the block. Okay. Now this small signal variation at the drain of your current source, in this particular case, how much small signal current variation will it cause in your transistor M2? That is the question. Okay. So in other words, you have some small signal variation here, a voltage. So this current ID, what is the small signal variation? So for that, what do? You go and take the help of the small signal model that we have derived. So since we are looking at DC type quantity, low frequency signals, we only look at the low frequency model of your MOSFET. So this is your gate terminal, this is an open thing, this is your VGS, let's say this is your S, this is your D, sorry, this is GM times VGS, and this is R naught. Okay. Now how do you do small signal analysis? You all would have studied in your third semester analog circuits. You basically go and set all your DC voltages to 0, and here what is the VGS, small signal VGS here? The small signal VGS is 0 here because it is a DC quantity. The stuff on the left hand side, it's purely DC, right? So small signal VGS is 0, alright. So which means that GM VGS is also 0. Okay. Now what are you left with? You are left with only R naught. Now the way you will calculate your output impedance is that you go and fix a test voltage source, okay, let's call it as VT, and you find out what is the test current that is flowing out of this test voltage source, okay, and your R out now is going to be given by VT by IT, alright. So I hope you remember this from your analog circuits course that you have done in probably your third semester of BTech. Now the way we calculate any impedance for that matter is, if you want, because right now we are looking at the output impedance, you stick a test voltage source there and you measure the test current that this is going to draw, and then you find out what is your output impedance. Now in this case your GM VGS is 0, so this can be redrawn as how much? How can it be redrawn? This is 0 volt, and so GM VGS is 0. If a current is 0, it is an open circuit. You only have R naught here and you have your VT here. So obviously VT by IT is nothing but R naught here. Okay. This is your output impedance of your single transistor current mirror, right? Okay. Now how do we do it for a cascode current mirror? We will do it in next class, but I would like you to just attempt it. So draw the small signal equivalent circuit. So you have your gate, you have your source, you have two GM VGS and R naught. Let's call it as R naught 1, GM VGS 1. This is gate 1, drain 1, and then you draw the next one here. So this becomes the source of the next transistor, right? This is D1, this is D2, this is R02, this is GM2, VGS2, and your gate here is grounded because small signal ground, this is G2, alright. Now you can derive your small signal output impedance. So we will do that in the next class. In the meantime, you can just try to attempt this. So any doubts, any questions?
Sir, that R not we derived for which circuit, sir, just now?
Oh, okay, this is a
Output
single
impedance.
transistor thing. Yeah. Let me just clear the confusion. Okay, this is for a single transistor, I mean, a simple current mirror. Okay. We wanted to find out what is the R out of this particular device. Is it clear?
Yes, sir.
Okay. So this, whatever we did here, I just wanted to, because the first small signal analysis we are doing for this course, I wanted to take it step by step. So this analysis is for this particular circuit. Okay. This whole portion is
Sir,
only DC, no AC, and you expect some small signal variation there. Okay. Any doubts?
sir,
Any
can't we
questions?
get this? So can't we get this R naught from that VDS ID plot
Yeah,
directly?
you can get it. The reason that basically it is the same. No, how do you calculate R naught here? R
So
naught is
the
calculated through
VDS.
that thing, right?
Yes, sir.
Yeah, it's essentially the same. This is the small signal way of you know uh, uh, hand analysis. There you look at the simulator. Basically, it's the same thing. But the moment you go for a cascode thing, here you'll get a little more complicated expression of the expression will be different, and the final value you can get it from your graph. Basically, from your simulation you can get the final value, but you'll also get the expression, and that gives us a lot of insight into how things work.
Okay, sir.
Okay. All right. Any other questions? Any doubts? So please do go ahead and download the LT Spice. It's a freeware. It's a free tool by Analog Devices. Please download it. I will put the 180 nanometer file today in Teams, and I'll also give a few exercises so that these basic plots you can generate. All right. Thanks everyone. Have a nice day.
Thank you, sir.
Thank you.